Well, my people, I hope we're doing well today. In this series of videos, we're going to be dealing with the related rate problems from three-dimensional geometry. So the first day we did exclusively Pythagorean theorem ones. Day 2 we did two-dimensional geometry, including a couple more Pythagorean theorem ones, but we dealt with circles and rectangles and triangles and all sorts of other shapes, areas and stuff like that. As we move into three-dimensional geometry, we're going to be dealing with volumes and surface areas and stuff like that. And oftentimes we'll have ones where there are too many variables and we have to do some substitution. And we did a couple of those examples in class. But thankfully there are some three-dimensional geometry ones that don't require some substitution. And it's largely cubes and spheres, because cubes and spheres are already only in terms of two variables, and therefore you don't have a third one that you need to do some substitution with. So let's go ahead and get started on this first one. The volume of a cube. If each edge of a cube is increasing at a constant rate of 3 centimeters per second, how fast is the volume of the cube increasing when the length, x, of the edge is 10 centimeters long? So, it's always good to draw what you're dealing with. And in this case, it's a cube, and thankfully we know cube is x by x by x. So the volume is simply x cubed. Now let's state our given. Now, it says the edge of each cube is increasing at a constant rate of 3 centimeters per second. So dx dt is increasing, so it's positive, 3 centimeters per second. All right, let's identify what question is being asked, what we're being asked to find. How fast is the volume of the cube increasing? So we're being asked for dv dt. Now, conditional information, right? The information that is not always true, but is the moment at which we're being asked for this given, is of course when the side is 10 centimeters long. So we're looking for when x is equal to 10 centimeters. Okay, well that's all well and dandy. Let's go ahead and differentiate. So we have dv dt, 3x squared dx dt. Now thankfully what we're looking for is already isolated, so really all we have to do is plug in. We have dx dt, it's a constant. We have x, that's the conditional information. So we simply need to plug in 10 centimeters and square it, and then multiply it by the original 3 and 3 centimeters per second. That is going to give us centimeters cubed per second. That's 3 is 9, times 100, 900, so we have 900 centimeters cubed per second. Okay, and then you would just write me a nice little sentence. It basically says the volume of the cube is increasing at 900 centimeters cubed per second at that moment. Okay, or when x is 10 centimeters long. So there you go. Ta-da! Okay, let's go ahead and do a sphere one, and we'll use these two to sort of warm us up to the rest of them. The radius of a sphere is increasing at a constant rate of 2 centimeters per minute. Find the rate of change of its surface area when its radius is 100 centimeters. Now, remember, it's easier sometimes for us to remember the volume formula than it is the surface area of a sphere. But the surface area of a sphere is 4 pi r squared. Almost like somebody took 4/3 pi r cubed and took the derivative. All right, so we have our given, and it is the fact that the radius, dr dt, is increasing positive 2 centimeters per minute. Okay, let's go ahead and draw that radius right here just so we can visualize it. So our question find the rate of change of its surface area. So I'm looking for dA dt. And the conditional information is find the rate of change of its surface area when the radius is 100 centimeters. So when the radius is 100 centimeters. Alrighty. We have dr dt, we have r. I don't think we're going to be missing anything. There's only two variables here, so let's go ahead and differentiate. We get 8 pi times r times dr dt. And again, thankfully, we already have the thing that we're looking for isolated right over here, so we don't have to do any analytic work. We just simply have to plug in and grind out our evaluation. So we have 100 centimeters that we plug in for r, and then we have 2 centimeters per minute. That's going to give us centimeters squared per minute. And it's you know, I'm not a science guy, so I'm not huge on keeping track of units and stuff like that. But in related rate problems, it really is helpful because it gives you an indication that you do indeed have all of the pieces that you need, if it makes sense, right? If the units tell me that what this arithmetic is spitting out is centimeters squared per minute, centimeters squared, that sounds like an area, right? And it's centimeters squared per minute. That's area per time. That sounds like dA dt. Okay, that means that I'm not missing anything in here, and that's, you know, it's really a good idea, especially just in terms of doing things intentionally, to have these sort of guiding ideas of what the answer should look like and what kind of units it should have as an indication that I'm on the right track, right? It's sort of like, it's like going bowling and putting the guardrails in, okay? It makes it just a little bit easier to hit the pins. And if we go along, you'll notice that if you actually start thinking like this, you'll actually wind up identifying times when something is missing. And that's kind of, you know, always better to figure that out before the test is graded than afterwards. 8 pi times 2, 16 pi. 16 pi times 100 is 1600 pi centimeters squared per minute. I'm not going to go ahead and write the sentence, but I will encourage you by saying you then need to write a sentence. Okay. Alrighty. Now we did a cone one in class, but if I'm not mistaken, we did sand coming off a conveyor belt and landing in a conical pile. And that's a classic one, but they also do problems where they take that cone and they flip it upside down as a water reservoir. Okay, so draining a conical reservoir. Water is flowing at a rate of 50 cubic meters per minute from a concrete conical reservoir, which means vertex down, right? Of base radius 45 meters and height of 6 meters. That's a really broad cone, so it's, right? It's not going to be to scale, obviously, but we'll do our best. Okay, yeah, that's a little bit off, but just pretend that it's perfect. Okay, so what we have here, gosh, that's really bad. We'll just deal with it. We have radius, and then we have the height. The height is 6 meters. Okay, the radius up here, okay, is 45 meters. Now, the water is flowing at a rate from a concrete. So basically, water is draining out, okay? So our given is that change in volume, that dV dt. Now remember, it is basically going out. So what is happening to the volume of water in the conical reservoir? Well, the volume is decreasing, and therefore it's negative 50 meters cubed per minute. How fast is the water level falling when the water is 5 meters deep? Okay, so the question, and we'll just deal with A right here. We'll look at B in just a moment. Okay, well, I mean, it's at that moment, so it's at the same moment. So it's the same conditional information. So I'm looking at A. How fast is the water level falling? So we'll call the water level H, right, for height. So dH dt is equal to what? And then, of course, we'll have dr dt for part B. The conditional information is basically when h is equal to 5 meters. Now, 5 meters is most of the way up, right? But you have to remember that when we're dealing with this, we have volume of a cone is pi over 3, so 1/3 pi r squared h. Because remember, a cone is kind of like a pyramid. It's basically 1/3 the base times the height, and of course, cone is just a infinitely sided pyramid, so it has the same volume formula. Now, or generally the same volume formula. What I have here is I have a formula of 3 unknowns. Okay, now that is a little bit of a difficulty, except if we actually take this idea right here and think of taking a cross section right across the middle of the reservoir just to take a picture of it, you should recognize the fact that there are going to be, and this is not going to be to scale, obviously, okay, the height right here, okay, is 6. The radius, that was a horrible one, but whatever, you get the idea, is 45. And wherever the water level is, if this right here is h and this right here is r, then we have similar right triangles, and we can come up with a proportion to actually plug in here. So we know that it's going to be 45 to 6, right? Radius to height is radius to height, and we're going to get 45h is equal to 6r. And here's the thing. I have to determine whether I want to change this whole thing into r or whether I want to change this whole thing into h. Well, I'm given h in the conditional information. Now, granted, I could go ahead and find the corresponding r, but since that's the case, let's go ahead and solve here for r, and then we'll plug in that h expression that is equivalent to r. So I have 45 over 6. They obviously both have a 3 in common, and therefore it's basically 15 halves. 15 halves h, right? Because this is 15 times 3 and this is 2 times 3. So we're going to take this expression right here and we're going to plug it in for this r. When I do so, I'm going to get 15 over 2h, and that's going to be squared. 15 squared is 225, okay? 225, however, is going to be cut by that 3, and because basically this is 3 times 5 squared. So it's 3 squared and 5 squared. One of the 3's cancels here, and I'm left with 3 times 25, which is 75. So I'm left with 75 pi. Nothing cuts the 4, though, the 2 when it's squared, so it just becomes 4, and that is h cubed. Now, ugly, yes, but doable and much preferable because now I have it in terms of 2 variables rather than 3. So let's go ahead and let's differentiate. And when I bring the 3 down, it's going to cut that 75 even more to 25 pi over 4 times h squared times dh dt. Now, my dv dt, let's go ahead and just solve for dh dt. That's going to be dv dt divided by 25, that was horrible, 25 pi over 4 h squared. Now dv dt is negative 50 meters cubed per minute. I'm running out of space here. And 25 pi over 4, so we'll just go ahead and keep that like that. And then h squared, so that becomes 5 meters squared. Well, in the end, what that becomes is this becomes 25, right? If this becomes 25 and this becomes meters squared, so 25 meters squared cancels with the 25 inside here and 2 of the meters here. And what I get is negative 2 meters per minute divided by this. So it's negative 2 times 4 over 25 pi meters per minute, or negative 8 over 25 pi meters per minute. And there we go. Okay. I have a couple more, and we'll keep making some videos until such time as I sort of either get sick of this, or I think you have sufficient knowledge, or I run out of problems. But if you have any questions, as always, please do shoot me an email. Bye.